Let's see. Just bear with me for 1 second. I don't want this to... There we go. Okay, perfect. We're live. Thank you so much for tuning in. Today, I'm going to cover a really interesting topic, which is the intersection between cryptography and cryptocurrency. When crypto came out initially, and still even today, a lot of people started calling cryptocurrency crypto. The term crypto was applied to cryptocurrency. And a lot of people who studied cryptography got very upset because they used to call cryptography crypto. And now when you say crypto, it makes people think about blockchains and decentralized protocols similar to Bitcoin and Ethereum. And there's a lot of research into cryptography that is completely unrelated to decentralized protocols. And unfortunately, there's a lot of bad things that are associated with this idea of decentralized cryptocurrencies, such as scams, FTX, all these different scandals, speculation, degens, all this stuff. The general public generally has a pretty negative conception of cryptocurrency. And I think there's a lot of resentment among cryptographers about the fact that they are now lumped in with cryptocurrency. Now, why is it called cryptocurrency, and why did people call it crypto? Well, cryptocurrency does use cryptography. It's just that you can either verify or keep certain bits of information secret. That's typically what cryptography does. So this is used in banking, in private messaging, throughout the internet, in the military. There's every single sector utilizes cryptography for security in one way or another. And cryptocurrency is one application of cryptography. However, first I want to say this is a legitimate concern that cryptographers have, and I could understand why. Crypto is a really cool short abbreviation of the field. So I could understand why they would be upset when everyone hears that they work in crypto or cryptography, and then they associate that with cryptocurrency, which maybe they have nothing to do with. I totally understand that and respect that. But what I'm going to argue here today is that cryptocurrency should be thought of as a subfield within cryptography, and that it is a completely legitimate innovation within the realm of what we should consider to be cryptography, and that cryptocurrency is actually a form of cryptography, and the consensus mechanisms used in cryptocurrency are very well paired with the other types of things that we do in cryptography. So I actually do recommend considering this to be one united field. And now, just as a disclaimer here, I'm not a mathematician, I am not a cryptographer, I am a layman, so I work in crypto, I'm vaguely aware of these concepts, so this is just my take on things. But I think that people will find it very interesting. And you might notice I called this stream part 1. Part 2 is going to take a little bit more research on my end. I'm going to end up relating this. I'm going to end up showing why. Like in this video, I'm going to kind of help you build an intuition for why cryptography is interesting, why cryptocurrency is interesting in the context of cryptography. But that's just going to spark your interest. It's not going to actually show you why it's useful. I mean, you will kind of get that, but there's a lot more to that argument. So at another time, I'm going to do a part 2 on this to follow up and show how basically cryptocurrency really fills a important hole in the overall capabilities of cryptography. And but for that, I think what we'll end up doing is we're going to have to research like volatility and a few other concepts like that. And I'm going to draw a lot of analogies to financial markets. And so I'll probably do some reaction videos coming soon to people who are in finance and work in these areas. So then we're kind of going to build up the understanding of these topics. And then I think at that point, I'll come back to this argument and do the part 2 of why cryptocurrency is cryptography. So really quick, if you're watching this, especially if you're on YouTube, please like this video. And I got my first like just a couple of days ago, or I think it was yesterday actually. I got my first like, and yeah, so thank you for those who are liking and subscribing and sharing. And I'm gonna continue to bring you this content every day. I mostly talk about technology and the impact that it has on society. So let's dive into this. Okay, so here we have two people, Alice and Bob. Now, let's imagine that we're starting out building a currency-based system. Like, let's just imagine we're building a cryptocurrency like Bitcoin. So we haven't started yet, so we don't know how to build this. We're just starting from scratch. We don't know anything about how to build it. So there is an initial allocation of, let's just work with dollars, because this is it's just a simple currency we can work with. So let's say that this is a system for tracking dollars, and we have the first person, the first user, Alice, is kind of like our Satoshi, and Alice, we're gonna just give Alice $20. So the starting balance of this system is that Alice has $20. Now, Bob is also a user, but Bob has $0. So we're just starting off and just giving all the dollars. There's $20 in the system, and we're giving it to Alice. So how could we build this? How could we build a trustless, verifiable currency? There's a lot of ideas, and we're not going to explore all the bad ones. I'll kind of give you a hint. One of the important things is cryptographic signatures. So we don't want to trust one person to track this, because if I'm recording down the transactions in a ledger, or PayPal is, or the US government, they could manipulate this ledger, and they can do whatever they want. We want to enforce this. So we want to have some sort of mathematical proof that everything was done properly. So, and something that can't be forged. So what we're going to do is we'll introduce this idea of cryptographic signatures. So Alice has a secret, Bob has a secret, and they use this, doesn't matter how it works, just realize that it does work. They use this old concept of cryptographic signatures to basically, it's similar to signing their name below the transaction. It's like you write a check and you sign your name. Kind of like that, except it's mathematically verifiable. It's not something that you can easily fake like a check. So let's just kind of imagine this scenario. There's only two people in this economy. So I'm just going to move my head here so you can see this whole thing. There's only two people in this economy. So this is going to be a pretty boring set of transactions. Alice has $20. This is the starting point. So no transactions have occurred yet. She starts off with $20. And then she sends $10 to Bob. And then Bob sends $5 back to Alice. So who knows why they did this, but this is what happened. And so now at each time when each of these were sent, Alice signed this statement right here. And so you know that as a fact that she put this out there. You know that Bob didn't just say, oh yeah, she gave me $10 and just trust me, bro. That's not what happened. Alice definitely signed this and sent it to Bob. This is a great system. Now we don't have to trust anybody who's keeping a record of this, because we know we can go back and we can look at the cryptographic signature in the archives, and we say, yeah, Alice did indeed send this money to Bob. It's proven, it's mathematical, it's great. So Alice makes a transaction. This represents a transaction. She sent $10 to Bob. Bob also signs his transaction and sends it back to Alice. So what's the problem here? Well, there's a big problem, and the problem is that we don't know the order that this happened. So this is a nice narrative of what happened, and it's very plausible. I mean, you can maybe do some investigation and think, well, how could it really be in any other order? But you don't absolutely know that it was in any other order. So for example, let's say it was in this order. Let's say Alice had $20, Bob had $0, and then Bob sent Alice $5. And then Alice sent Bob $10. Now, you might say, how could Bob send Alice $5? But remember, all that Bob was doing was creating a transaction. And he signed this statement saying, I'm sending Alice $5. So that's all that he did. So that would be an invalid transaction. So for example, if Alice sent $100 and she only has 20, that would also be invalid. So there's this idea of a valid transaction and an invalid transaction. But how do you know if the transaction is valid or invalid? You have to look at the state. So you have to look at what is Alice's current balance, and then you have to see relative to that if the transaction that she makes is valid. So perhaps Bob did sign this statement and Alice did sign this statement, but we don't know what order it was in. So if Bob happened to sign this before Alice sent this, then it would have never been valid in the first place. And in that case, what should have happened is he tried to send $5, it didn't work, and then Alice sent him $10. Like maybe he thought he also had $20, and so he was just doing, I'll do a test transaction and send you 5. And then he got back the error saying, oh, actually, you didn't have any money. She's the only one who got the money. You didn't get any. She has to send you some before you can use it. So then she sends him 10. Like you can imagine some scenario with this. So what's the difference? Let's go through the difference in these scenarios. Okay, so this is the real scenario that we're talking about. So right here, let's just start off. Alice has 20 and Bob has 0. Okay, that's the start. Now, Alice sends Bob $10. Okay, so Alice spends 10, so now she goes down to 10, and now Bob has 10. Now they both have 10. Then Bob sends Alice $5. So Bob goes down by 5, and Alice goes up by 5. So this is the final balance when it's in this order. Now let's do something different here. Okay, now this is a new scenario, so let's start over. So we're still starting with Alice having $20 and Bob having $0. Now, Bob gives Alice $5. This is an invalid transaction. Okay, so the balances are the same. Nothing happened. He tried to give her $5, but he didn't have $5. So that didn't work. Okay, then Alice can give Bob $10, and now they have 10. So I should have saved this result, but what it was before, I'm just gonna, I'll just write this right side by side so it's very clear. Under scenario 1, Alice ended up with $15 and Bob ended up with $5. And under scenario 2, Alice ended up with $10 and Bob ended up with $10. These are different scenarios. So now there's 2 divergent forks and 2 divergent possibilities, and we don't know. There's literally no way to tell which one is valid. Maybe you can just trust Alice and Bob. Perhaps maybe they're very trustworthy people. Maybe whatever they said is the truth and you just know it. But as this scales to be used across society, you can't trust everybody. And this becomes a big problem. Okay, so what is a solution to this? Well, one solution is that you can have a chain of different transactions where you specify the order in each incremental transaction. So for example, you can you could just kind of have these pointers going from this one to that one, this one to that one. Although technically the way that it would work is I have these arrows backwards. Really, how the way it would work is, given the starting place of $20, Alice would say, okay, this is the first transaction, and it would point back to that starting balance, and it would say, in this new balance, it would say, look, this is what I'm acknowledging is as the truth. I'm starting off with $10, and when I send this $10, I'm actually saying this is my first transaction after having had $20. So there's a reference in this transaction where Alice sends the $10 to Bob back to this original statement. And just, I want to reverse the arrow direction here because this is probably in some sense more accurate. I'm going to reverse this arrow direction as well. Okay, so this transaction is signed, and in the body of the transaction, the thing that is signed is also a reference to the history. So now this is saying, hey, we got this, there's a starting balance, and this is the first transaction. And then this one that Bob sends, it says, hey, I did this after Alice sent me $10, so this is why I have $10 to send. Now, all of a sudden, there is no ambiguity here. And this really solves the problem that we were talking about. But unfortunately, it doesn't fully solve the problem, because now, just as an example, let's just introduce another person named Carol into this economy. What if now Bob sent Alice $5, but then Bob also sent Carol $6? I'm just going to do this in this reverse arrow direction. So when Bob, so everyone knows this is like canon. Alice sent Bob $10. This is fact. But then Bob sent Alice $5 and Carol $6. And in doing that, Bob didn't do this arrow to here. He didn't reference Carol going back to Alice. Instead, he referenced he referenced Alice. Now, maybe you can't trust Bob. Maybe Bob was trying to scam both Alice and Carol. Maybe they were at a farmer's market and he was trying to buy from both of their stalls. And so he sent them the payment, and he knew that if he did it quickly enough, they wouldn't notice that he had already sent all his money. And they could just check it, and there's some kind of, they wouldn't necessarily, we don't need to go too much into the specifics of this hypothetical currency. There's a lot of ways that you can do this type of a thing. And the point is, though, that he put out these two forks out there. So he put in a scenario in which he sent Alice $5 and one in which he sent Carol $6. And unfortunately, he only had $10. So he spent more money than he had. So in this case, he had $10 and he spent $6 to Carol. And so then if he tries to spend another $5, that he only had $4 left at that point. But so that $5 is too much. And similarly, if he would have sent it to Alice first, he would have only had $5 left, and he would try to send it to Carol. And that is, again, he's trying to send $6 to Carol. This is going to be invalid. So the question is, how do you resolve this? So let's say that there's a dispute and they come to you, and all you have is this paper trail and maybe their testimony. Carol says, he sent me the money first. Alice said, he sent me the money first. Bob sent both of them the money around the same time. We don't know who he sent it first to. And Alice and Carol are trying to claim their payments in bankruptcy court, let's say. How do you know which one's correct? Is it possible to know which one is correct? Well, no, not without changing the protocol. If this is all the evidence that you don't have video footage or anything else that will prove to you what happened, and you just have these two claims on the money, somebody is going to lose $1. Because, or all their money, depending on how you resolve it. At most, someone's going to, or at least one person's going to lose $1. That has to happen, because there's only so much money in the system. And there's no way, there's no information encoded into these transactions that can determine which one of these is canonical and who actually deserves the money. So this is also a lacking system. Now, what I want to show you is that let's kind of think about this as like a tree of possibilities. And I'm just going to reveal kind of like what's over here on the side. Let me move my face so that, oh no, that's not. I'm trying to get this so you can see the whole diagram. Okay, I moved my face over here. So, all right. So basically, let's think about this again. Alice is starting off with $20. Okay, cool. Now, what's interesting is that At this point, in the beginning, we actually have no uncertainty about any new transaction. So think about this. Each of these is a possible set of scenarios. Maybe Alice gave Bob $10 and Bob gave Alice $5, then Bob gave Carol $5. Or Bob could have given Alice another $5. Or Alice could have given Alice gave Bob $10 and Bob gave Carol $6. Then Carol gave Alice $1, or Carol gave Alice $6. So all of these things are, each one of these, I'm not going to do this for all of them, but this is each a valid path. I guess I am going to just put all these arrows here. These are all valid paths, and they're mutually exclusive forks. So this is the incremental new transactions, and any one of these could be valid. We don't know. And, but let's think about, it's a little bit more interesting than that. So we're thinking about all of these transactions, and in the beginning, when Alice has all of the money, we actually know the validity of all of these incoming transactions. Because there's only, for example, we know that Bob does not have $5 because Alice has $20 and he has $0. That's the starting balance. So before Alice gives Bob any money, we know for sure that Bob couldn't give $5 to Carol. Similarly, we know that Bob couldn't give $5 to Alice. It's not possible because Bob doesn't have any money. We know this as a fact. Similarly, we know Carol couldn't give Alice $1, and we know Carol couldn't give Alice $6 either. Bob and Carol have no money. We know that these are invalid transactions. And we also know, let's say that there was a transaction coming in with Alice spending $10, giving it to Bob. We know Alice has $20. So we know, just given that this 10 is less than 20, we know that that's also valid. And we know that if Alice gave Bob more than $20, let's say 30, we know that would be invalid. So we have a very high degree of certainty about what is valid. And really, there's only one fork. It's canon. There's only one possible viable fork. Now, let's say that Alice gives Bob $10. Now, at that point, now we know that this is in play because Bob has money. So let's just look at these incremental new transactions. Both of these are plausible. Now that Bob has some money, he could give it to Carol or he could give it to Alice. These are both potentially legitimate. But what we definitely know is that Carol could not give Alice anything because Carol never got anything. So when we have there's this idea of state growth. So as there are more values stored in state and state becomes larger, it's not just one balance keeping track of how much money Alice has, it's now two keeping track of Bob. This increases more uncertainty. So before we knew everything, we knew what was valid, what wasn't. We had no uncertainty. Now that Bob has some dollars, now there is a little bit of uncertainty. We don't know which one of these is correct because they both can't be correct. It's not possible because since Bob had given it to Alice, then he didn't have, he only has $5 left to give, so he can't do both of these transactions that total 10. So now we don't really know what's going on between these. We know these are definitely not legit, but we don't know about which one of these is accurate. Now, let's imagine Alice starts with Alice starts off with 20. Alice gives Bob 10. Bob gives Carol $6. Now there are 3 different values tracked in the state, and now you can kind of see how there could be even more, there's more potential for contention. So now any of these forks could actually be valid. Protocol, which is not rigorous math or anything formal. This is just like a kind of a heuristic way of thinking about it. Basically, I'm kind of saying, and this is not 100% true because the number of forks is not really like that. It's not. It doesn't expand like this. There's not like there's 2 forks. There's not like 2 divergent forks on every single state transition or anything like that. But I'm kind of just saying approximately, if you think about it, like when there was when there was only state was only with one person, there was no ambiguity. There was just one fork. It was just the canonical fork. We knew what was true. As we had 2 people, now there were 2 possibilities. Then with 3 people, there was 4 possibilities. And this is, again, I didn't even extrapolate this trend, but I'm kind of reading into this that this is like an exponential number of forks, like the number of forks doubles as the state grows. Now, again, this is not literally true, but this is almost like the conception. I'm kind of just trying to draw an analogy to the conceptual space of all possible forks. And what I'm saying is that the state is like a log of the incremental new transactions. It scales with the log of the incremental new transactions that are contentious, which is the different forks. And so if you know anything about entropy, you'll kind of start to see that this resembles mathematically something like entropy. And so in a system like this, now you have cryptography, you're using cryptography, you've proven everything, this is mathematical. You have a great system, you have a blockchain, you have transactions and digital signatures and everything, you're doing it all right. But you still have this entropy growing in the system. So in other words, the cryptography isn't actually very useful because as this scales, as more transactions occur, as more untrusted people enter this network, as it gets to internet scale, and you're not able to arbitrate or coordinate across very large groups, now the entropy grows in the system and it can become basically useless over time as over time you have absolutely no idea what is the true state of the ledger. So now I want to do an experiment. Okay, so I took a picture of some eggs. Let's see. Yeah, here's 5 pictures of eggs. Sorry, let me move this up here. Okay, so you can see it. So these eggs, I took this in some order, and there is I use a random number generator to shuffle them. So this is not in the original order that I took the photos. Now, I'm going to tell you a few things about this. This was effectively a closed system. No eggs entered or left. So all this picture captures the totality of the eggs that were involved in this experiment. So I never took a new egg and brought it in. I never took an old egg and took it out, or I didn't do anything like that. This was a closed system. Tell me, just take a guess, just as an experiment, just take a guess, what order was this in? Was it 1, 2, 4, 3, 6, or 5? Why did I say 6? I don't know why I said that. I don't know. Was it 2, 4, 3, 1, 5? I don't know. Was it 1, 2, 3, 4, 5? I don't know. Just guess. Try and figure it out. Go for it. I'm just giving you a sec. Write it down. Let's just see if you can get it. Look at it. Try and figure it out. Okay, I'm gonna cut you off. I don't want you to waste your time because I have no idea which order this is in. I really don't. I don't remember. There's no way to tell. These are just, so this is similar to the transactions that we were talking about. We don't know, there's no way to determine what was the ordering. Like if we had a bunch of different arrangements of these, we wouldn't know which one was true and which one was not. We can think of plausible arrangements, but we don't have any proof that it was a certain way. Now, if I told you it was just 1, 2, 3, 4, 5 in order, maybe you would believe me. There's no way you can verify. There's no reason to doubt me if I tell you that, but I will tell you, I promise, that I did use a random number generator. So what are the answers? Well, did you write down your answer so you can check if it was right? Well, I will reveal it now. Okay, let's just move this. So this was the fourth one. This was the first one. This was the second one. This was the fifth one. And this was the third. So first I took this one, then I took that one, then this one, and then that one, and then that one. Okay. I mean, how would you know that? How would I know that? We wouldn't. Now, I don't think you got it. And the reason why I don't think you got this right is because there were 5 factorial, there's 5 images, so there's 5 factorial ways of arranging these images, which equals 5 times 4, which is 20, times 3, which is 60, times 2, which is 120, times 1, which is 120. 120 possible arrangements. I didn't think you got that. That's less than a 1% chance. It's possible you did. Congratulations. But you probably didn't get this right. Now, I'm going to show you another example with these eggs. Similar constraints. This was a closed system, no eggs left, no eggs were added. It's just the eggs were contained in this area and nothing changed. What is the order of these images? One sec, I'm gonna move my image again so you can see it fully. What was the order of this? Try and figure it out. Spend a few seconds trying to figure out what was the order of these images. Give you a second. I want you to really figure this one out. This one's possible. Just don't give up. Like, think about it for a second. Think about it. Just waiting. Okay. I hope you figured it out by now. If not, pause and then continue watching. So, okay. I did not write down the numbers where this was, like this, for example, there's no number underneath it. Like the other ones, there was numbers. Because I know instantly what the order was of this. It's very clear. So first, the eggs were unbroken. Oh, great. My face keeps getting in the way. One second. I can move my face over here because this is a useless zone. Okay. So first, the eggs were unbroken, obviously. Then I broke one egg, but the yolk was intact and not scrambled. Then I scrambled the egg. The yolk is no longer intact. Then I broke the next egg. And then I'll just move this. Then I scrambled the final egg. So now the yolk is no longer intact. This was the order. It's obvious. I literally could not convince you that there's any other order. I mean, if you believed that, you would be a sucker. I mean, this is obviously true. You can't unscramble an egg. You can't uncrack an eggshell. Like, how would you do that? That's ridiculous. This is absolutely, mathematically, the answer. Like, this is beyond a shadow of a doubt, the order. And I just knew that. I didn't need to write it down. You knew that. I knew that. And yet, how do we know this? It was a 1 in 120 chance. It's still 5 images. So how did we know that this was the order? It's just an image. It's just an image of an egg. Like, what's the difference? How do we know? Well, because encoded in these images was a system that had increasing entropy. So there are these stages of breaking an egg where entropy is introduced along the way. And we know that these are basically non-reversible processes. And I want to be really clear that I am drawing an analogy here. When I'm going to relate this to blockchain, I want to draw an important distinction between the information theoretic version of entropy and then the normal physics, classical physics definition of entropy. These are different things, but they're really deeply related. This is entropy, and we know that across time, these processes cannot be reversed. And so as a result, this is something that intuitively we understand really well, and we're able to just check and verifiably see the entropy increase at each point in each image. These are fundamentally the same thing as the above images here. They're just eggs. They're just pictures of eggs. It's fundamentally the same thing. But this is just the eggs are going through a process whereby entropy is increasing. And so here, there was uncertainty about the ordering of these images. And as you add more, the uncertainty, which is the entropy, was increasing. And here, assuming that this process continues in a manageable, measurable way, the entropy would not increase as we add more images. Like going from this image, this is completely clear. Adding this final image did not increase uncertainty. There was no added entropy by adding an additional image. And in a sense, what was happening here, and again, this is metaphorical, and it's a complicated subject, and I'm not claiming to be an expert, but in a sense, the entropy in this collection of images was outsourced to the entropy of the eggs. Now, this is essentially what is done with a cryptocurrency. So like taking Bitcoin as a really clear example of this. The analogy gets a little bit harder when you come to proof of stake. So I'm not even going to cover that. But with Bitcoin, you can actually draw a very good analogy here, because essentially this, and so it will, whatever order the transactions are inside of the block is going to be kind of arbitrary, but it's something that everyone can decide on. And then each block has a hash, and the hash references the previous block, so there's an order. But then what happens is it uses a hash function, which itself is a function that contains a lot of entropy. So a hash function is a function that basically you put something in, and the results on the outside, so you put something in and then the output it's not actually random, it's effectively random. It's something where you would not be able to predict where what the input generated. You wouldn't be able to go backwards. So if I put in some message, you wouldn't be able to see the hash and then know what that message was. It's easy for me to calculate the output, but you don't know what the input is. In other words, it's not easily reversible, kind of like cracking an egg. You put something in a hash function, it's like cracking an egg. You can't go back, it's not reversible. And this is a direct thing that's actually measured by cryptographers when they're developing hash functions, is the entropy. And that and if something has high entropy, it's going to be a good hash function, because there's going to be uncertainty introduced into where the input maps to, and it's going to be uniformly distributed. So it's not going to all be like clustered in around some value. It's going to be any output is possible on a roughly even distribution from any given input. And so the hash function actually is like cracking eggs. And whenever you don't know what output you're going to create when you put an input into a hash function. So the way that Bitcoin mining works is you build the block, you decide what's going to be the order of this chunk of transactions, and then you have a nonce, which is a value inside of the block. And that nonce, you can update the block anytime, you don't have to stick with the original bundle, but by simply updating the nonce, you're basically doing a random number generator and churning out different values in the nonce. And the hash function will then give you different hashes. And basically what you want is a specially formatted hash. And there's just a certain probability that you're going to get this type of a hash. And if you get a hash and it's not in that format, it doesn't count. It doesn't work. But if you do happen to find a hash that follows the format for the proof of work algorithm, then that hash is counted. So there's a probabilistic angle there. So there's no way that someone can figure out what nonce to put in order to get the special hash that they need. They can't go backwards. They can only go forward. So the only thing that they can do is build the block and just try a bunch of times. And basically, we know that because of the entropy of the SHA-2 hash system, we know that basically there's a certain amount of entropy that had to be burned through in the proof of work in order to have a chain of a certain length. And when you have this thing called a weight, it's basically how much work went into the chain. When you have this concept of weight, like a weight is like the cumulative entropy that has been run through the system, and like similarly to with 1.5 eggs being crushed. So the weight is like a measure of the entropy. And I think there's some really interesting philosophical and scientific things physicists could dive into in how, there is something very interesting about how this is at the union of like thermodynamics and information theory, and you're putting energy into these miners and having, they're running this hash function, but you're literally using energy as well. And there's probably some interesting insights to draw from that. That's a bit beyond my level of expertise. But the bottom line is that is basically a very similar system. So in summary, what blockchains are doing with consensus is they are finding a way to reduce this entropy. They're outsourcing the entropy. They're kind of like transmuting the entropy from the state growth or the entropy that's inherent as you go over time and have more contentious forks. And they're checkpointing that into a verifiable mathematical function that we know has entropy, which is SHA-2. If for whatever reason someone could basically predict SHA-2 and reverse the hash and just basically come up with a hash whenever they need it, that would break Bitcoin. It would break the consensus model, because it's predicated on the dynamics of people mining and having based on a higher chance of coming up with a hash based on how much hash power they have. And so that would completely break Bitcoin. So that is, in a sense, how cryptocurrency consensus adds to the capabilities of cryptography. When we're talking about building things with cryptography, we're talking about things that you can prove. You can prove signatures, you can verify signatures, you can you can now do ZK proofs where you prove the results of computations. The issue is that even though you're proving all these things and like the proof of this is super valuable, the problem with it is that the entropy will still grow in whatever system that you're using. And there are two ways of dealing with this. One could be to just like trust somebody to resolve it. There's a lot of problems with that. We can analyze that scenario way more next time. But it's completely valid to have a system that will basically checkpoint the state into a system where we have a verifiable amount of entropy and we can reason about those properties, and in doing so we can actually reduce the entropy in the system. So that's kind of my starting pitch for why cryptography, or why cryptocurrency is a form of cryptography. I will come back to this series. We're going to talk more about this in part 2, but that will not be tomorrow. I'm going to do a bit more research and go from there. And we'll do this research together. I'm going to do some reactions to some relevant videos, and we're going to build up this theoretical understanding, and then I will return to this subject and continue making this case. Thank you everybody for tuning in. I will see you